Most developers I talk to hit the same wall. Claude does something remarkable, then something embarrassing, and they have no idea why. That's not random. It's completely predictable once you understand what the model's actually doing. By the end of this, you'll be able to look at any output and reason accurately about why it's right, wrong, or confidently wrong. You've met the Claude app, the modes, the features, the place your context lives. This episode goes one level down to the model underneath all of it. It's the conceptual ground floor everything else builds on. By the end, you'll have a correct mental model of what a large language model actually is, what it does well, where it breaks down, and why. No benchmarks, no hype. Just the frame you need to stop being surprised and start being effective. Let's start with the one fact that explains everything else. A large language model is trained on vast amounts of text, and what it learns to do, at its core, is predict what comes next. That's the mechanism, not a database you query, not a person who knows things, a pattern completion engine operating at extraordinary scale and sophistication. You already use a simpler version of this every day. When your phone suggests the next word as you type a message, that's next token prediction. A large language model is the same kind of thing, but trained on so much more text, with so much more capacity that entirely new capabilities emerge from that scale. It can reason over a legal document. It can spot a bug in your code. It can explain a concept 5 different ways until one lands. All of that falls out of the same basic mechanism. Predict what comes next at scale. Here's where the analogy has to stop, though. The phone keyboard is predicting from a handful of words. Claude is predicting from a context window containing your entire conversation, any files you've pasted in, and patterns learned from an enormous body of text. Same kind of thing, radically different capability. Don't let the autocomplete comparison make you underestimate it, but don't let the impressive outputs make you forget the mechanism. This is the load-bearing section. Everything else in this episode depends on understanding this one distinction. When the model produces an answer, it's generating the most plausible continuation of the text it has seen so far. Not the most accurate continuation, the most plausible one. Most of the time, those align because the training data contained a lot of accurate text, and accurate statements are statistically common. But plausible and true are not the same thing. That gap is where things go wrong. Think about what it means for the model to know something, say a historical date, or how a specific API works. It doesn't know it the way you know your phone number. It knows it in the sense that it saw that fact stated consistently across a large amount of text, so generating that fact is the highest probability continuation when the topic comes up. That's a real and useful kind of knowledge, but it has a specific failure mode. When the model hallucinates, when it gives you a confident, fluent, completely wrong answer, it isn't malfunctioning. It's doing exactly what it was trained to do, generating a plausible-sounding continuation. In a region where plausible diverges from correct, you get confident nonsense. The model has no internal alarm that fires when it doesn't know something. It just keeps generating. Now go back to the 2 examples from the opening. The bug finding worked because code patterns, including common bugs and their explanations, appeared extensively in training data. When you show it a piece of code with that class of problem, generating the correct diagnosis is the high probability path. The arithmetic failed because the model isn't running a calculator. It's pattern matching over text that looks like arithmetic. It's often right on simple cases because simple arithmetic is common in training data. But it can be confidently wrong because it doesn't verify, it continues. One mechanism, 2 very different outcomes depending on whether plausible and correct happen to align. Here's the second foundational concept. The model has no memory outside the current conversation. None. Open a new chat and ask it about something you discussed last week. It has no idea what you're talking about. You're a stranger. The context window is everything the model can see right now. Your messages, its responses, and anything you've pasted in. That's the complete picture. If a piece of information isn't in that window, it doesn't exist as far as the model is concerned. This is why giving the model the right context isn't a nice to have. It's the entire job. The model can only reason over what's in front of it. Some interfaces add persistence features. In the Claude app, projects let you maintain shared context, instructions, files, across multiple conversations. At the time of recording, that works by injecting that context into the window at the start of each conversation, not by the model having persistent memory in some deeper sense. Worth verifying current behavior in the app because these features evolve. But the underlying principle holds. The model sees text in a window. Persistence is about what gets put into that window automatically. None of this is an argument for using AI less. The strengths are real, and you should understand them as clearly as the limitations. Language and transformation tasks are where this mechanism genuinely shines. Drafting, editing, summarizing, rewriting something for a different audience, translating tone. These are pattern completion problems, and a model trained on enormous amounts of human writing is very good at them. Reasoning over material you provide is another strong suit. If the answer is inferable from text in the context window, the model often does it well. You've given it the raw material. It can draw connections and synthesize. Code is a real strength because the training data included vast amounts of code with explanations, documentation, and examples of common patterns, including common problems and their fixes. That's why the bug detection worked. To make this concrete, take a dense technical paragraph and ask Claude to explain it in plain language. It handles this well, consistently. That's the mechanism working in your favor. Pattern completion over text that includes enormous amounts of examples of explanation and translation across complexity levels. There are 4 failure modes you need to have named in your head before you work with any language model. First, hallucination. Confident, fluent, wrong answers. Especially dangerous on specific facts. Citations, proper nouns, exact numbers, anything requiring precise recall. The model doesn't know it's wrong. It sounds exactly the same as when it's right. Second, prompt sensitivity. Small changes in how you phrase a question can meaningfully shift the answer. This is actually useful. You can guide the model toward better outputs by framing things carefully, but it also means you can accidentally mislead it. If your prompt contains an assumption that isn't true, the model will often follow that assumption rather than correct it. Third, no live knowledge of the world. The model's training has a cutoff. It doesn't know what happened last month. The exact cutoff varies by model and version. Check the current documentation for whatever you're working with. But the principle is universal. For anything time-sensitive, treat it as potentially outdated until you verify. Fourth, weak exact computation. Arithmetic, counting characters, exact string matching. The base language model attempts these and is often wrong for the exact reason we covered. It's pattern matching, not computing. This isn't a fundamental limitation of AI systems. Tools fix it. When Claude has access to a code execution environment, it can write and run code that produces exact answers. The base model alone cannot reliably do it. Know what you're working with. Knowing the failure modes is half the job. Here's the other half. The concrete moves Anthropic actually recommends to keep them in check, and they're refreshingly simple. First, give the model an out. Tell it, right in the prompt, that it's allowed to say, "I don't know," instead of guessing. That single line measurably cuts hallucinations because you've made admitting uncertainty a valid answer instead of forcing a confident one. Second, when you're working from a document, ask it to pull the exact quotes it's relying on, word for word before it answers, and to cite them. Now the answer is anchored to text that's genuinely in front of it, and you can check the receipts. Third, when accuracy matters more than range, tell it to use only the material you've given it, not its general training. You shrink the space where plausible but wrong can sneak in. None of these are tricks. They're you working with the mechanism. You can't make the model verify itself, but you can shape the task so the truthful path is also the most plausible one. 3 mistakes I see constantly, even from experienced developers. The first is trusting a confident answer without checking. Confidence is not a signal of accuracy. It's a property of the generation mechanism. Get in the habit of verifying factual claims before they leave your draft. The second is assuming the model remembers earlier conversations. It doesn't. Every new chat is a blank slate. If context from a previous session matters, you need to bring it in explicitly. The third is assuming it knows recent events. It doesn't know what happened last week. For anything current, use a source that does. Let's close with what has to stick. A large language model predicts the most plausible next token. It is not a knowledge store, and plausible is not the same as true. Hallucination isn't a malfunction. It's the mechanism operating in territory where plausible and correct diverge. The model has no memory outside the current context window. If it's not in the window, it doesn't exist. The strengths are real: language, transformation, reasoning over provided material, code patterns. The failure modes are specific and predictable: hallucination, prompt sensitivity, no live knowledge, weak exact computation. None of this is random. It's all downstream of the mechanism. Here's your exercise, and I mean actually do this one because it demonstrates the failure mode better than any explanation can. Write a paragraph, any paragraph, something you have handy, and ask Claude to count how many times the letter E appears. Then count manually. Notice that it gives you a number fluently and confidently. Notice how close or far off it is. That's the mechanism doing exactly what it's designed to do in a task where pattern completion is the wrong tool for the job. Or ask it a specific factual question about something that happened recently. Watch how it responds. Watch whether it signals uncertainty or just continues generating. Understanding how it fails is just as important as understanding how it succeeds. If this framing is new to you, the single most useful thing you can do right now is go interact with the model differently, with this mechanism in mind, and see what you notice. Next episode, we turn this understanding into a way of working, a simple 4-part framework for collaborating with AI well, effectively, and responsibly. If you want that when it drops, subscribe and you'll get it. See you there.